Welcome back. Today we're going to talk about conditional probability and independence. So when we talk about conditional probability and independence, conditional probability is the probability that something happens given that something else happened. And so I'm going to divide this box in half. And let's go to work here. Conditional probability. Looks like this. It's the probability of A, and then I have a slash here, and then B. And so this line right here literally means given that. Okay, so that's literally the probability of A given that B. And this becomes a fraction because we are considering a single event happening in light of another event. And so our B is going to become our denominator, because it's always going to be over the probability of B happening, because B is our limiting factor, right? So given that B happened, so that limits everybody who didn't have A happen. So given that B happened becomes our denominator. And then on top goes the probability of A and B. And why is that? Well, because if B is a limiting factor, then A and B had to happen to put it on top, meaning you couldn't just do probability of A, because it's given that B happened, okay? And we'll look at that a little bit more down below when we start to work on this particular problem. And this is where we're starting to talk about independent events. Okay, or independence. And independence in probability is when knowing one event has occurred or has not occurred does not affect the probability of the second event. Okay, so what does this actually mean? I want you to consider two events here. Being a junior at a school and owning a cell phone. So here's how this would work. Let's just say you looked at the probability of being a junior, and the probability of owning a cell phone at a given school. So let's say I go to my school and I take a survey of all the students in the school, and I find that there is, a 94% of people own a cell phone. And I've got this sneaking suspicion that perhaps my junior class, for whatever reason, they just don't own as many cell phones. Maybe this is more probable for like a 7th grade class or something. But if we're thinking about junior, so let's just say we have this hunch that maybe the junior class has less cell phone usage. Well, really what we're asking is, are they independent of one another? Meaning, does being a junior impact the percentage of people that own a cell phone? And so what I do is I take the whole school, and I know that there's 94% of people that own a cell phone. And then I ask my juniors, what percent of you own a cell phone? And I find that 94% of students own a cell phone or close to there. For the purposes of this example, what that means is that those two events are independent, meaning it doesn't matter whether you're a junior or not. You're in the school, it's 94%, or you're a junior, they're independent because they have the same likelihood of happening whether or not you are a junior. How does that manifest itself in the mathematics? Well, it would mean that the probability of A is equal to the probability of A given that B is equal to the probability of A given that B complement. So whether you are a junior, the probability of being a cell phone owner and the probability that you own a cell phone given that you're a junior, those things are equal. And if this is true, so if this is true, then A and B are independent. So maybe your head is spinning there and you're like, well, that I don't I'm not exactly sure what that means. Let's do a little example here, and you can kind of get an idea of what we're evaluating against one another. So here is a big giant list of data that talks about a Pew Research study that selected 100 mothers from age 40 to 44 in 3 different years, 1976, 1994, and 2014. And they asked each mother how many children they have, and then the two-way table summarized these results. Again, a good rule of thumb for checking your understanding like this would be to pause it and try to do it on your own, or get as far as you can, and then come back and see what I have to say about it and check your answer. So if you want to pause right now, this is a good spot. If not, then I'm just going to keep rolling, and you can watch along as we work through this example. So take a look here. Here's our years. So what they asked was, how many kids do you have? So this many people said 1, 2, 3, 4 plus in each of our given years. And so really what, like, comparing across the totals for the given years, right? So how many mothers of this 100 that were picked in the given year? So 11 and 76, 21, and then 22. And then we can kind of see, maybe there's some significant statistic here. We don't really know yet, but 40 of those moms had 4 plus children in 1976, only 13 in 1994, and then 13 in 2014. And so we're looking at this, and I only point that out to say, there's a difference in these statistics. So we have reason to look at how these events might be independent. So suppose we randomly select one of the survey respondents, define event C. So C is they have 4 or more children, S is 1976, N is 1994, and F is 2014. Good rule of thumb when you're doing probability problems, you want to define those variables, because that's going to make it easier to write out, like, for example, probability of C given that S, instead of probability of having 4 or more children given that you were in 1976. So just kind of a shorthand way to make things easy. So I'm going to actually write that down. So probability of C given that S is the probability of 4 plus children given that. Remember, this line means given that. So given that, it was 1976. So that's kind of shorthand for that. So probability of 4 plus children given that it was in 1976. So 4 plus children, 1976, follow the columns, boom. So in this case, this is 40 over 100. Interpret the value in context. So given that the mother was surveyed in 1976, there was a 40% chance she had 4 plus children. Okay, 40% chance she had 4 plus children. Given that the chosen mother was not surveyed in 1976, what's the probability that she has 4 or more children? So this is going to be the complement of that 1976. So not in 1976, if S is 1976, not in 1996, or 1976 would be S sub C. So given that S sub C, and we still are measuring that 4 or more children, so that was going to be C. So this is the probability of C, given that S complement, is going to be equal to, 4 plus children. So I'm following this row here. And it's not this row, but it's everything else. So that's going to be 1994 or 2014. So that's the probability of C, given that 1994 or 2014. And there's a way to write that, right? So the probability of C given that N or F. So I could sort of shorthand it like that. And that's going to be 13 over 100 plus 13 over 100, which is 26 over 100, or equal to 0.13. Again, probability, giving that in an unreduced fraction to remind ourselves of how many people we actually ask. So actually it's 200, right? So that would be 0.13 there. So are the events surveyed in 1976 and 4 or more children independent? Explain. So no, they are not. And this is kind of what we talked about above, right? So if they were surveyed in 1976, are they equally likely to have 4 or more children, whether or not they were in 1976? Well, the question is, does the year make the difference? So is 4 or more children the same in all years, or are they dependent on one another? Meaning, if you're asked in 1976, does whether or not you had 4 or more children depend on what year you were asked in? So does it depend on whether you're asked in 1976 or not? And so what we would say here is no, they're not independent, because mothers in 1976 that were surveyed, are more likely to have 4+ children than the mothers not surveyed in 1976. And the shorthand version of this would be that the probability of 4 or more children, given that it was 1976, does not equal the probability of having 4 or more children, given that you were not in 1976. Okay? The concept of independence is going to come up repeatedly in this course, and so hopefully you can kind of tie that to this example. But the question that you really are asking is, does it matter whether you were in a certain group or not? Does that affect the percent that fulfilled the other criteria? And so kind of look for those independence problems. When they ask if they're independent, you're going to be testing 2 probabilities against one another. And if they're the same, then they're independent, meaning it doesn't matter which kind of other criteria you had. But if they're different, then it depended on which other criteria you had, and that's what makes them not independent. So thanks for watching, guys, and we will see you next time.